Okay. So we're all talking about the same thing. Let's just review. An indefinite integral. All right, an indefinite integral is the integral of f of x dx. We call that indefinite because the bounds aren't supplied. It doesn't translate to area because we don't know where to start and we don't know where to stop. All right, so what's the opposite of an indefinite integral? A definite integral, right? And so a definite integral does translate to area. Because you know you start at A and you stop at B. Bless you. Okay. And that can translate to area. Unless what happens in between A and B? What would be a problem? Okay, some kind of discontinuity. So like a gap or a jump or an infinite asymptotic. If something was a problem, okay. No, a cusp, we can still find area under a cusp because it's continuous. A cusp is not differentiable, okay, but yeah, if there's a discontinuity, then we have a problem. Okay, that is called an improper integral, and there are a couple different kinds. All right, so let's specify in our definite integral a note as long as f of x is continuous. On A to B. Okay, so an improper integral. Couple problems that we could run into. One would be an integral from A to B where a discontinuity exists, is present on the interval from A to B. So that would be considered an improper integral. You can't find the area because there's a big break there or a hole or an asymptote or something. Okay, that would be one kind of improper integral. Another kind of improper integral would be A to infinity or infinity to B. Negative infinity, excuse me. So how do you find the area then? Okay, if you start at A but you just go on forever, is it possible to find the area? Or on the other side, if you're coming from the left and you're going from negative infinity to B and you stop at B, how do you find the area? Those are both considered improper integrals. Okay. It is possible to find the area for some of those integrals, and we call that converging area. Okay. Other times, it is not possible and the area diverges, and so it's not possible to find it. We call that a divergent integral. So we're going to talk about convergent versus divergent integrals. Okay, so some improper integrals still converge to a defined value for area, others don't. So semicolon, others still diverge. And so we just have to check. Okay. So suppose we didn't want to go all the way to infinity. Let's start with that option. Let's start with we're going to rewrite them to make them workable. Let's start with the option where we start at a and we go to infinity of f of x dx. Okay, the legal way to get around that, it almost feels like cheating, but not quite. Okay, we want to stop just before we get to infinity. Okay, so as close to infinity as we can get without actually getting there. What is that usually called when you're talking about things that are as close as you could possibly get, but you don't actually do it? Okay, if we could define infinity, that would be one way to do it. Is there another way to get super close to something but don't touch it? A limit, right? Okay, so what we want to do is we want to change the upper bound to a defined value of b, and then we want to say that b is approaching infinity. It's not getting there, but it's approaching infinity. And so that's our way of getting around it. Like, I'm not going to infinity, I'm just going close to infinity of f of x dx. And so then we evaluate the integral, and then we apply the limit to the value of the integral. So you can do that on the flip side as well. If you've got negative infinity and then stopping at b, you can rewrite that as a to b. But then the limit on that one, what's going to approach what? A will approach negative infinity. So it will be close to negative infinity, just not all the way there. All right. What if you have an undefined, a point of discontinuity, okay, in the middle? So what if you have a to b of f of x? So the ends are fine, okay, with a discontinuity at x equals c. So say there's a problem in the middle of your interval. Okay, so then you're going to have to split this up. So you would say, okay, then let's go from A to C, and then let's go from C to B. So first you break it up according to the laws of integrals, which says you can split it at a number, but we don't actually want to go to C. Okay, so we need to pick something other than the actual value of C. Because C is a number. C is like 2. Okay, so pick another variable. Sure, K, J, Z, W, pick something. Okay, pick a variable. I like Q. And the limit of Q will be approaching what number? C from what direction? From the left. And then on the other side, oops, leave my space, I'll go from Q to B, and my limit of Q will be approaching C from the right. So it's just like playing the game, right? It's kind of skirting around the rules. And we say, you know, don't cross that boundary line. It's like a football player who just barely gets his toe in there, barely. You know, they've got all this instant replay, and they've got the ball, just the nose of the ball just barely crosses the line. Okay, that's what we're talking about here, as close as you can without. All right, so let's actually, that's how we're going to tackle that. Okay, so to answer Cassidy's question, I now have 5 examples where we're going to consider like one of every situation. Okay, here we go. Let's evaluate 1 to infinity of 1 over x dx. Okay, does 1 over x have a discontinuity? Yes, at 0. Is that discontinuity within my bounds? Okay, so I don't have to worry about that this time. We'll come back to that. Maybe we'll do that one where we are. But okay, so for this one, we are just going to rewrite 1, and what should my upper limit be? B. And the limit will be as b approaches infinity. Okay, so we're just going to do this as normal. We're going to evaluate our limit, evaluate our integral just with a limit notation in front of it. So what is the antiderivative of 1 over x? Natural log, and we remember the absolute value of x plus the constant c going from 1 to b. Yeah, our bounds are our intervals positive right now. So, okay, so then we have the limit as b approaches infinity, and we just plop our bounds in. So we're going to have the natural log of b, which is a positive number, minus the natural log of 1. And we all remember what the natural log of 1 is, right? Okay, so this will be the limit as b approaches infinity of, the only thing I have left is the natural log of b. Okay, and then I'm going to drop infinity into that now that I've evaluated the antiderivative. And so I get the natural log of infinity, which is infinity, which means this is still a divergent integral because the value of the area is infinite. There is no specified value, and so this is still considered a divergent improper integral. But we will next see a convergent improper integral. Yeah?
Is there a way to determine if the integral is divergent or convergent according to the graph? Because the graph of this function
goes on forever.
Forever and goes to 0.
But not, see, we're gonna, you would think yes, but there are some times where, like there's something called Gabriel's horn. If you Google it, it might be interesting for you to read about. Here's one. Okay, Gabriel's horn is it's like a, it starts out looking like a French horn and then it comes down, like this. They call it, okay. So it has infinite, if I get this right, infinite volume but finite surface area. It's a paradox. I think I remember that right. It has infinite volume.
Oh, isn't that weird? It looks like a
and
thing.
yes, okay.
Oh, wait.
So they say it holds infinite amount of water, so it has infinite volume, but you can paint it with you can paint the outside with a finite amount of paint. Like it has a finite surface area. I think is that what it says? We better pause this while I think about it. I'm going to do a convergent one next. Okay, let's go from negative infinity to positive infinity. Okay, improper, not indefinite. Okay, how much area is under there? Let's just look at the graph a minute before we tackle it from figure out what happens to the area. Okay. We need to separate this because we're going to need a limit for the bottom and we're going to need a limit for the top, and we can't do a double limit on the same problem, so we're going to split it. You can pick a random, because this has all real numbers. You just separate this at any, I usually just pick 0. That's easiest. So we're going to first split this up at 0. 0 is defined, so it's fine for me to split it there. If you don't like 0, then pick the letter A. Okay. Now I want to replace both infinities with a limit approaching that particular one. So with my first equation, I'll replace that and I'll use a for that. So a is going to approach negative infinity. So my integral now goes from a to 0. And then I need a separate limit describing the numerator. So my limit is going to be b approaching positive infinity, and that one's going to go from 0 to b. This is not going to be twice the work, though, because they both have the same antiderivative. What is the antiderivative of 1 over 1 plus x squared? Inverse tangent. So I get the limit as a approaches negative infinity of the inverse tangent of x plus c going from a to 0. And then I get the same antiderivative with a different limit. This time the limit goes from b to positive infinity of the inverse tangent of x plus c. That one is going from 0 to b. Can you fast forward ahead in your mind a little bit and see what's going to happen to both times I plug in 0? Maybe. We'll check. Okay. So I'm going to get the limit as a approaches negative infinity of, first I plug in 0. Oops. So the inverse tangent of 0 minus the inverse tangent of a. And then in the second limit, I'll have the limit with my bounds plugged in. And I will have the inverse tangent of b minus the inverse tangent of 0. Okay, are you with me so far? Okay, now plug infinity and negative infinity in. So I start with the tangent inverse of 0 minus the tangent inverse of negative infinity plus the tangent inverse of positive infinity minus the tangent inverse of 0. So I started with the inverse tangent of 0. I ended with the inverse tangent of 0. No matter what number I would have picked to split my integral at, that would have happened, right? Whether if I'd picked 1 or negative 1 or pi or any number, that would have happened where the front and the back were the same. And so those two cancel each other out. Okay, now, do you remember your inverse trig? Negative parentheses. What is the inverse tangent of negative infinity? So that means when's the first time that tangent within its domain period, which goes from negative pi over 2. That's the first time that tangent achieves a value of negative infinity. You can picture it either on I usually do a graph in my head, picture a graph in my head. And then plus, when is the first time, that tangent achieves a value of positive infinity? Pi halves. And so I end up with a double negative, pi halves plus pi halves equals pi. This is a convergent integral. That means that the original integral represented area that converges to pi. It won't necessarily be pi, but it will never be more than pi, is converging to an area value of pi. Because at some point it doesn't gain the area. The negligible area is so small that it will never be, that's the limit of your area. You would think that we're gaining enough area that we would have infinite area, but it doesn't. It converges to pi. Okay, let's try another one. Okay, how about from negative infinity to positive infinity of e to the x? Does that have a convergent amount of area? Okay, well, at least in the other one, both sides went down, right? Here you've got one side that's down, but one side that's up. So your gut is going to tell you diverge. Okay, but you got to show me that it diverges. All right, so where do you want to split this one? 0 again? Okay. All right. Sure. So we'll say the limit as b approaches, no, as a approaches negative infinity. And then we would have from a to 0 of e to the x dx. And then the second one would be the limit as b approached positive infinity, and we'll go from 0 to b of e to the x dx. And just recognize that 0 is an arbitrary value. You could pick any constant because the domain of this is all real numbers. And so any constant you want to pick would be fine. All right, this one's going to be easier because the antiderivative of e to the x is e to the x. So we'll have the limit as a approaches negative infinity of the antiderivative of e to the x plus c on the bounds that go from a to 0. And then the limit as b approaches infinity of the antiderivative of e to the x plus c as the bounds go from 0 to b. And so we can really kind of do all of this at once. E to the 0 minus e to the a, but e to the a was negative infinity, plus e to the b, but e to the b is positive infinity, and then minus e to the 0. So I've got e to the 0 in the front, e to the 0 in the back. What is negative e to the negative infinity? Okay, right, it's negative 1 over e to the positive infinity plus e to the infinity. So we're looking at 0 plus infinity, which diverges. Which our gut kind of told us because one end of the graph was asymptotic and the other end of the graph was not. Okay. All right, 2 more. That's okay. And then you'll have a little bit of time to work. Okay, how about this integral? Oops. 2 over x squared plus 4x plus 3 dx, going from 0 to infinity. All right, where are the discontinuities? Okay, so the discontinuities here, you would think about it in its factored form. So 0 to infinity of 2 over x plus 1 and x plus 3 dx. So it does have 2 discontinuities, but the discontinuities aren't within the bounds. So I can go right to integrating that.
A over that.
This is partial fractions.
Oh no.
Yeah, it's all mixed in there. It's all mixed in. All right, so we need partial fractions. I already worked it out. Do you want me to work it out with you or just tell you the answer?
We know. Is partial fractions where you use the A and the B?
Yes.
Okay. I like them, I just don't want to do them right now.
Okay. All right, so the partial fractions, A turns out to be 1 over x plus 1. B turns out to be negative 1, so negative 1 over x plus 3 dx. All right, so there's your partial fractions. Okay, my lower bound is going to stay 0. What will my upper bound change to? I think B is better at the top, but it would be fine if you did A, as long as whatever you pick goes to infinity. Okay, partial fractions is done. Okay, and then we'll do our antiderivative. So bless. The antiderivative of 1 over x plus 1 is the natural log of the absolute value of x plus 1 minus the natural log of the absolute value of x plus 3 plus c going from 0 to b. Can what? Sure. Okay, so this is a subtraction. The rule of natural logs is that when you subtract 2 of them, it will be the natural log of the absolute value of x plus 1 over x plus 3 plus c from 0 to b. Alright, what's the rule when you're taking a limit approaching infinity? Divide by the highest power of x. Alright, so the natural log of 1 plus 1 over x over 1 plus 3 over x plus c. Highest power of x, which is just x in this case. So you divide each term by x. So x divided by x, 1 divided by x, x divided by x, and 3 divided by x. Okay, so now, can we do it all at the same time? Can we plug in b and plug in infinity all at the same time? So we're going to have the natural log of 1 plus b, which is approaching infinity, over 1 plus b again, which is approaching infinity, minus can you what? Well, you don't want to use you don't want to use 0. The 0. We should have split this up. Yeah, we should plug in our bounds first because we want to go back to the other version. We want this 0 plus 1 over 0 plus 3. There. We go back to the other one so we can plug 0 in.
So it's minus 11 over 3.
It's not cheating, we just...
Well, it can become infinity.
No, it doesn't become, yeah. We're going back to the undivided by x. We only want to divide by x for the part that we were plugging infinity in. We don't want to divide by x for the other one. Okay, so ultimately what do we get? The natural log of 1 minus the natural log of okay, the natural log of 1 is 0. The negative natural log of 1/3 is the same as the positive natural log of 3. Did I do that too fast? Or we could write it like this. We could say minus the natural log of 1 minus the natural log of 3. We could write it like that if you want the 1/3, right? And so if you distribute the negative, we get ln 3, which means ultimately what about this original integral? It converged. The area converged to the natural log of 3. Okay, one more. Yes, you did. I believe in you. I use it in real life every day, all the time.
Oh, but do we?
In math,
You're in engineering, they're like, hey, what happens if we go to infinity? You're like, what?
Outside of a studying context, I don't know if this is applicable.
I think they're gonna use it in the NASA.
Yeah.
Because they-
Multivariate calculus
Space
and beyond. All right, last one.
Is this problem as long as the last one?
Yeah.
I don't like that. Oh, yeah.
Right? Which was what we were like, nah.
Oh my. Do you have to use the
No,
lip
no,
it?
lip
The tabular.
No. I refuse. Nope, not,
What is this?
can't, nope, won't do it. I take back my statement that I believe in myself. Not too much, can't do it. I know, I just give it.
Catherine would do this. I've seen her do it. Okay. It's a product which you're recognizing already that we have to integrate by parts. I don't know how you organize yourself, but I'll just do something like that. Tabular. We have a polynomial. We've got.
It's only one. So it will be the same thing.
You get the same. Yeah, you only I would only do tabular if you had to do a repeated integration by parts. This one, it only takes one level because it's just x. But okay. All right. So yes, according to Lippitt, x is our polynomial, which means e to the negative x is not. Okay, the derivative of x, dx. The antiderivative of e to the negative x is negative e to the negative. You can do it how you want. Whatever works for you. No. Okay. We'll do our plus c, yes. So now we've got, we've got x, negative x, e to the negative x. Okay, then what? Okay, so
technically
plus
e to the negative x.
All of that is to the limit b to infinity.
What?
okay.
No.
Around all of that, yes.
Okay.
After we evaluate our last integral, then we'll have our plus c. Okay. 1 to b as, yeah. So we've got negative x, e to the negative x, and then our next antiderivative is minus e to the negative x, and then plus c. And then our bounds are 1 to, should we keep it infinity or switch it to b right now? B, and then we will have the limit in front of that as b approaches infinity.
We will have to put the bound for the first step.
Yeah, the bounds apply to the first step. They're all in there.
But we will have to show it.
I'm sure there are bounds right here from 1 to b, and there are bounds here, 1 to b. Okay. Go team. All right. It's not all going to be infinity. All right. Negative b, e to the negative b, minus e to the negative b, plus 1 e to the first, plus e to the negative first.
Oh, okay. The 2 over e. I don't know, plus
space.
I
Okay.
know, but we don't know that.
Oh, why? Because I hadn't plugged infinity. You could put infinity in your places if you want. But if I put infinity, change it to an infinity.
It becomes 0.
Right, well what happens when I put infinity on the b, when I get e to the negative infinity for both of them, I'm going to get, this is 0, that's 0.
How's that zero?
Because when you put infinity, e to the negative infinity.
Yeah, because e to the exponent is higher.
Okay, you can do L'Hopital to that little part.
Isn't it, can you just tell us by Neffel? What is it again?
Enfepel?
Enfepel.
No.
So e
Enfepel has to do with growth rates. We're not talking about growth rates right here.
Wait, hold it. No, but you would
How
know.
is e graphed? I forgot.
Oh, is it?
Okay, so e to the negative infinity is
0.
0.
Because you're way down at the
And e
end.
to positive infinity is positive infinity.
Yeah.
Gosh.
Wait. No.
All right, we'll back up. I'll back
You
up.
don't have to back.
Are you okay with this being 0?
Yeah.
Just not the one next to it. Okay, so then for this one, we'll say it's negative, negative b over e to the negative b. Okay, that's indeterminate, yes?
Yes.
Oh, right, over e to the positive b. Because you get infinity over infinity. Okay, so then I would need L'Hopital on that one. So then I would have negative 1 over e to the b. And then I plug infinity into that. And now I get 0. So now you're okay with it being 0?
Yeah.
I would never be able
On
to
like
do
the
that.
first one, is that E plus B?
Oh, it was a positive. It was a negative that I changed to a positive.
It's E to the B.
E to the positive b.
Thank you, okay. That was so, that was like weird, like.
Yeah, it worked if you watched me write it, but then if you looked later and didn't see me write it, the answer's not 0. Okay?
Oh, I meant 2 over e.
Okay, because the answer's not 0. Those two are 0, but the other ones are 1 over e and another 1 over e. So the answer is 2 over e, which means it converges.
Okay.